Like freeze a whole bunch of different things.
See,
melt
just
them
do
in a
some
whole bunch of
experiments, huh?
different Things and see if those properties hold out.
Well, so I've thought about it. And has anyone else kind of thought about it? You're like, too busy with homework.
Oh, the oil one?
The ice cube with the water, and then what happens if we, now, when I started thinking about it, we said, we're gonna freeze something else. And it's like, you need to know the properties of how it affects it, because a lot of things, even a lot of liquids, when you freeze them, they still contract.
Everything but water.
Yeah, water is like the exception. Now we can put things in the water that will change it, like salt water, change the density, and you still freeze salt water. It's gotta get really cold. So I started thinking about what happens if I put a freshwater ice cube in salt water. Okay, and I'm not going to tell you the answer. Maybe we'll sign that as a homework problem. Because it's basic fluid properties right there. So, all right. Oh, I forget to. And once again, you think, well, that, understanding things like that shouldn't be too hard. But they are. And we'll get to the Bernoulli equation or the energy equation. I don't think we'll make it by today. But when we get there, I remember thinking as a student, after seeing the derivation and using it, I thought, wow, this is really not that hard. And yet I struggled to do a lot of the problems. And then, I go back to grad school and I'm thinking, well, gosh, if Bernoulli could do it, why don't I have the Savage equation type of thing? But Bernoulli spent an awful lot of time. Now, Bernoulli was actually a family. There's several, if you get into the literature, there's several things attributed to Bernoulli, and it turns out there's multiple Bernoullis, but the one that came up with the energy equation, yeah, it wasn't just boom, there it is, and it took a long time to solve some of those things. So don't beat yourself up for saying, wow, why did I not understand this, or that's so simple. It's like I remember one of my favorite professors, his concept was everything is easy when you understand it, right? But it's the getting to the understanding part that's the difficult part. Okay, why isn't that? There we go. Okay, those on screen, can you, I don't know if I shared my screen, let's do this. I really hate how this does this, but. It shows my screen share. There we go. All right. Okay, Lou, can you see the overhead? See my hand there? Thumbs up or give me a yes? Thumbs up. Okay, great. Thank you. All right. So we finished up talking about buoyancy, the principle of buoyancy. And now I want to move, remember we're going through the fundamental principles of fluid mechanics, those 6 principles. We've kind of moved from fluid properties that included pressure, and now I briefly want to go through momentum. All right. Now, momentum is fascinating because there's a lot of things we can do with momentum, but when we break it down to a 1D problem and we simplify it, there's quite a bit more that we can do with it. And that's where I want to take it to right now. I'm not going to go through the derivation of the momentum equation. Once again, that was in your fluids course. I just want to jump right to the equation that we normally use. That is this. Got some new erasable pens. And let's see how these things do. momentum. Okay, or conservation momentum. Those online does that show up okay? You see that okay?
Yes.
All right. So if you remember, we went through, well, first off, let's spend a couple minutes to talk about just what is momentum. In terms of a physical object, when you go to physics, how do they describe momentum? Or what's the equation that describes momentum? Mass times velocity, right? It's pretty simple. And a lot of times in physics, they like to use a billiards ball. You know, you got one ball rolling and it's got certain mass, it's moving with a certain linear velocity. And I would note we are dealing with linear momentum, not angular momentum, which is another, objects that spin have energy as well, or have momentum. But linear mass times velocity, but we get back to the same problem that we had before with fluids. With a solid object, we can define it as a point, a car, center of gravity, and it has mass and it's moving linear momentum. With fluids, they're constantly mixing, so the momentum of one packet of fluid can be completely different than the packet of another packet of fluid. And they're constantly exchanging momentum, right? And this is what we call turbulence in fluids. I like to use the analogy of two trains on parallel tracks. And we can look at them either going in the same direction or in opposite directions. Let's look at them going the same direction. One is really big and heavy, and it's moving at a slow velocity. And the other one right next to it is really light and fast. But as these two trains pass each other, they're coal-powered trains. And as they pass each other, there's a number of people standing on these trains, and they pass coal back and forth. And this coal is equal weight. They just happen to be in, a little round ball of coal that weighs the same. And as one on the slow train throws one over to one on the fast train, at the same time someone on the fast train is throwing one back over the slow train. And there's quite a few people doing this, and it's instantaneous, well, not instantaneous, but it's like pretty fast. All of a sudden it occurs at the same time. So the mass of both of these stays relatively the same. So my question for you is, what happens when that occurs to each of these trains? And nothing? They just keep moving forward? What does the low velocity particles of coal due to the high velocity train, and what does the high velocity particles of coal do to the slow moving train? Another example here, okay? Medicine ball. Everyone knows what a medicine ball is, a big weighted ball, used for strength training. So you and your buddy are out for a little stroll. You're each carrying a medicine ball. Well, let's even simplify it. Let's say, hey, your buddy's carrying a medicine ball. Your buddy is running and you're walking. Your buddy comes running up behind you and just kind of yells, here, catch this. And they're running really fast and they throw a medicine ball and you reach out and grab it. What's that going to do to you? They're going fast, you're going slow. You grab that medicine ball, which has a significant weight to it, right? You grab that, isn't that going to do that to you? It's going to pull you forward. Okay, the same thing with the trains. The slow train is going to speed up and the fast train is going to slow down because we had a mass exchange of momentum. Okay, so that's what momentum does in fluids, is it transfers momentum between fluid particles, and some particles speed up, others slow down. And turbulence inside of fluids is a momentum transfer process. All right. Now we try to simplify our life, and we go into the Reynolds transport theorem and talk about conservation of momentum, and we boil it down to when we are steady state. And let's see, does it have to be a fixed control volume to meet this criteria? Yeah, fixed control volume. All right. And when we do all that, when we make all those assumptions, oh, and it's incompressible. So we're dealing with water here. We do all that, then we get the equation. The sum of the forces is, the sum of the forces acting on the control volume is equal to the momentum flux. So remember, we're not doing just mass times velocity. We're doing the momentum flux. How much mass is coming with that momentum? So it is the sum of rho Q V going out minus the sum of rho Q V going in. Okay. And typically, because forces are a vector and momentum is a vector, then we break this down into its component parts. So in other words, we would say the sum of the forces in the x direction acting on the control volume is equal to the sum of rho Q V in the x direction going out minus the sum of rho Q V in the x direction going in. Now, if you want to see the derivation of this, once again, crack open a fluids book. Now, there's one little tricky thing you got to be careful about. Well, I guess we could boil it down into one, and that is the sign convention. Vectors have direction. So when we use this, we have to define a sign, a coordinate system, right? So we define coordinate system. So if we do the standard XY coordinate system and say that those are in the positive directions, then we now have direction for not only the forces, but also for the velocity. And if we have direction for velocity, we also have direction for area, because maybe I'm getting ahead of myself here. We haven't talked about conservation of mass yet, have we? So let's take a little break here from momentum and talk about conservation of mass. Now, this really doesn't take us too long in the extent that we're going to look at. I'm going to jump back to these pans. I don't know, it might be a little better, but conservation of mass. Now remember that Q, being the volumetric flow rate, is equal to the integral of the velocity integrated across the area. This is across the control surface. Now, this is a two-dimensional integral because surface is 2D. So technically, I could put two integrals there because we're crossing X and Y. But what I'm saying here is if we have the velocity going across some plane right here, so this represents some area. Not drawn very well. And we have a velocity vector there, okay? We can define then the differential flow rate, dq, the differential going across this differential element, d, that has area dA, is equal to then the velocity that is normal with the area. So we have the velocity dotted with the unit normal times then the differential area. Let's just talk about this for a minute. Because once again, this is a simple concept once you understand it. If I have the wind blowing perpendicular, or if I have the wind blowing in this direction, and it's parallel to a window, wind's going right here and the window's right here, look out the window this way, how much of that air is going through the window? Absolute zero, right? But if I have the wind going perpendicular to the window, everything's going through the window. And likewise, if the wind approaches that window at some angle, then only part of it is going through the window. And the part that is going through the window is defined, so I should put velocity vector dotted with unit normal. The unit normal then is the unit normal coming out of that area. Okay, and so I'm only going to capture the part that is perpendicular to my surface that is going across it. All right, but if we assume that things are one-dimensional, then that makes our life easy, and we can boil the conservation of mass equation down to the principle then that Q is equal to velocity times area, right? So the flow crossing an area at whatever velocity times the area gives me the volumetric flow rate. And I can, if I know Q in is equal to Q out, then I can say that V in times A in is equal to V out times A out. So if I have a pipe that has an expansion to it, so if I have a pipe and it's an 8-inch pipe, so coming in right here, 8-inch pipe, velocity is equal to 10 feet per second. And this expands then over to a, let's say a 12-inch pipe. All right. Can I find the velocity going out? Sure, it's pretty basic, right? Use the diameter, calculate the area, calculate the flow rate in, divide by the area, the flow out, and now I have the velocity going out. So there's a simple concept. All right. One other thing with conservation of mass is that if I dot the velocity with the unit normal, and they are in opposite directions, what is the sign that I get? So back up to this picture right here. Velocity vector coming in, my unit normal is pointing out. When I dot two vectors that are in the opposite direction, what do I get? What is the sign? I have two options, right? Positive, negative. So is it positive or is it negative? You guys are starting to worry me here a little bit. It's negative, right? Because if it was going in the same direction, if I have a vector going off in this direction and I want to find the component of that vector in the x direction, and I dot this f with I, I'm going to get the component of that force vector in this direction. That's going to be positive. But if I have a vector here, I don't care if it's force or not, going in that direction, and I dot it with a negative I direction, well, the resulting is going to be f, or negative fi, right? It has to be a negative value. So that's what I'm trying to point out here, because this is going to take us back to the momentum equation. The velocity dotted with the unit normal of the area gives me a negative value, all right? So now that we've got conservation of mass done on a basic level, this is what we need for right now. Q is equal to VA, V1 times area 1 is equal to V2 times A2, right? Now that we have that concept, we come back to momentum, and we say we define the coordinate system, and we also look at, so define the coordinate system, and then we look at the direction of the flow. And that's where this negative sign comes from. We've got to be really careful with it, because we have two velocities when we're dealing with momentum. We have this velocity right there, and we have the velocity built into flow rate. And if we don't get the sign correct, then we're going to be in trouble. All right. So if I have, let's do another example here. If I have a random, well, let's see, should do a random control volume, or let's do a pipeline, because I think physically you can relate to a pipeline here. I've got a pipeline and I've got flow coming in. I've got flow going out. So I'm going against the standard normal convention, which is left to right. Which is kind of interesting. I had a colleague that tested this once. He gave students a homework problem with the standard convention of the flow going left to right. Then on the exam, he just reversed the flow with the same numbers, right to left, about half the class. So how do we do this? And it's not that I'm laughing at students. I think I'd be part of the half that said, what? This is, what's going on here, right? Because we just get so used to something. Flow's going in and out there, and if I use my coordinate system here, X and Y in the positive direction, now when I go to write my momentum equation, all right? So I'm going to put a force right here. Here's my force. There's friction on the fluid acting on the side walls of the pipe. So I have to hold that pipe in place. Something has to hold that pipe in place. Otherwise, the pipe would just move due to the moving fluid. So this force is holding that pipe in place, all right? So I have one force here. We call that F sub x. So when I do my momentum equation, I'm going to get F of x. That's the only force that I'm worried about right here. Oh, thank you. Okay. And that has to equal rho Q V out minus rho Q V in. Okay. However, this would be wrong because the flow rate here defines the out part. Okay, Q out. Well, Q out with the unit normal is positive. So I've got that right, it's positive, but Q out, this velocity vector is negative. So I would come in here and put a negative sign. And over here, Q in is negative because, you know, here's my area that's crossing, and my unit normal is going in this direction. So it would be negative value. And that's where that negative comes from right there, that standard notation. But this Vn is going in the negative direction, so I would say that now is positive. Then I could solve my equation to figure out, you know, what's the kind of force I need to hold this thing. So I have to take into account both whether the fluid is entering the fluid, or the fluid is entering the control volume or leaving. If it is entering, then it's a negative. And if it is leaving, it's a positive. But then I have to take into account the velocity, and that is a function of my coordinate system. If I flipped my coordinate system around here, would I change those? I would leave these how they were originally, and you're right. Then I would have to make that a negative, right? I should have done that, but you know, you get the idea. So the second velocity and the forces, their direction is a function of your coordinate system. So make sure that you take that into account, all right? Now, we're not going to do too much with the momentum equation in this course, but I do want to do one thing. I want you to understand the principle of a thrust block. You want to tell me what a thrust block is?
Usually in pipe works where you have like angles and bends and stuff, you have to put some sort of anchor into the pipe because the fluid moving through it can actually force the pipe to go in a direction to possibly blow the ends off the fitting.
Good, good. That's absolutely correct. When you change direction in a fluid, you got to remember in basic fluids, we talked about the full derivative, right? So this is a little side note, full derivative. The change in velocity with respect to time is equal to the local change in velocity with respect to time, plus the velocity in the x direction times the change in velocity with respect to x, plus the velocity in the y direction times the change in velocity with respect to y, plus the change in the z direction times the change in the velocity with respect to z. Because in fluids, not only is it a change in time that can create that can make a velocity accelerate, but a change in position can make the velocity accelerate. Flow goes around a curve. We call that a centrifugal acceleration, right? If you have a centrifugal acceleration, you have a force. Anytime you have an acceleration, you have a force. There may be no change in time. You have a steady flow, 10 gallons per minute going through your pipeline. But you run it through a curve, and now there is a change in direction. And you can look at this anyway. In order to get that change in direction to occur, you know, the pipe has to act on the fluid, and the fluid, due to Newton's third law, right, equal and opposite reactions, is going to be pushing back on the pipe. So, or is that the first law? See, I can't remember now. Oh well, one of Newton's, the first or the third. We know the second one pretty well, right? Let's see, the first is an object in motion tends to want to stay in motion. Yeah, so it's the third law. All right, there. So the third law, equal and opposite reaction. So if the fluid goes around a bend, a change in direction is a acceleration. So if there's acceleration, there's a force. So as Scott noted, if we have an elbow or a T or something that changes direction, we now have to hold that in place. And it's pretty significant. It can be a pretty significant force, all right? Now, two quick embarrassing stories on my part. And there's a part two to one of these stories, but I'll save that for pipelines. But so I'm putting in this irrigation pipeline. We're building our house, and we moved here to Pocatello. And my neighbor, we wanted to share a line for partway between our two lots, kind of save a little bit of money. And so we took the pipeline coming off the community irrigation system, and we ran a T down right between our two lots. And behind the T, now, so the flow, imagine this, the flow's coming from underneath the road, turns a 90 and comes over, and we stick a T right there, and then the pipeline continues to go the other direction. But we stick a T right there to send it down between our two lots. And we're kind of in a rush, trying to save a little bit of money, so I take a great big rock, and I throw the great big rock behind that T. So give you a little bit of a picture here. So here's the flow coming in. We have this T that goes out like that. And then it keeps going down. But the majority of the flow, this is really a dead end down here. So the flow has to come and turn and go down this direction. So I put this great big rock right there. And I assumed that this was native soil being a little more cohesive. I thought, well, that's good, right? So when the flow comes down here and it makes that change in direction, I need something to hold it in place. So we got all put together. We said, let's pressure test this before we fill it back in. And turned the water on, and all of a sudden, just water came spraying everywhere. This was probably about it's only a 4-inch line. It was probably about a 35, 40-pound rock that I threw down in there. And it was right up against the native soil cut of the trench. We just took that rock and shoved it back into that trench. Popped open right here, separated the pipe, and water shooting everywhere. Wow. He knows what I do for a living too. I was pretty embarrassed. So we had to wait for it to dry out a little bit, so we get down in there, and we put a couple sacks of concrete down in there, all right, to then hold it a little bit better. And then over in our fluids lab down in the ERC, if you've ever been down there, so when I was building that, had a graduate student, we were putting the pipeline together. And when you run a pump, it's not good to run a pump what's called deadhead. And when we hit pumps, you'll see that as well. So you don't want the pump to be on and the flow's not going anywhere. So we have what's called a bypass line. So if we have the pipeline to our system or whatever we're testing shut off, well, the water we open up a valve, a little bit of a crack, and it goes back and through that valve and down into the tank, and the pump just recirculates it, right? So we got it all put together, and my graduate student standing somewhat close to that pipe, not real close, about 10 feet away. And I go to turn on the pump. It's a 60 horsepower pump. It's a big pump. It's a 12-inch pipeline. It's not a 2-inch pipeline. It's a 12-inch pipeline. We can move a lot of flow through this thing. And I flip that pump on for the first time, and I look over and I see the pipeline, this bypass pipeline that we have going over to drop it back into our sump, just lifting off the ground, because it went over to the over to the tank and turned 90 degrees and was shooting straight down. So it was like a rocket, just went right off. Boom. And so, I mean, it hadn't moved, it just started moving. I was like, oh, flipped it off, but too late. The momentum carried it up. It busted the T right, just sheared that thing right off. It flipped it big around, went over and hit the wall, and put this big old gash in the wall. And I looked at my grad student and said, well, at least I didn't kill you. And here's what happened, is we'd done all the calculations of our whole system, and everything was good. Then, without thinking, we thought, oh, we're going to save a little money. It was a 12-inch pipeline from the whole system, except for this return line. We thought, well, why do we, after we'd already designed it, we thought, why are we putting in a 12-inch here? Let's go ahead and just put in, right after the elbow, let's put in a reducer, take it down to an 8-inch pipe, and save some money. Because an 8-inch valve is a lot cheaper than a 12-inch valve, and is also a lot lighter. And the volume of water in an 8-inch pipe is considerably less than the volume in a 12-inch pipe. So the calculations worked out that there was sufficient weight with the valve, the pipe, and the water to hold that thing on the ground until we changed it to an 8-inch pipe. Then it took off like a rocket. So lesson learned, if you make a change, make sure you check your calculations, right? I was embarrassed there too. So we strapped everything down. Went back in, fixed it, which by the way, I learned that you can actually unglue PVC pipe. I'd never, White's looking at me like, what are you, nuts? Yeah, that's what I thought too, right? Like, I don't have money to cut this pipe off and replace the whole thing. It was glued, And it's like, how are we gonna do this? I knew I had to replace the T, and a 12-inch T is not cheap. It's like, how are we gonna do this? Well, you can actually go in, I thought it welded the pipe together. But you can go in with a heat gun. And first off, you have to saw a little crack down through it. And you go with a heat gun and you can heat it up, and you can grab it with a pair of like needle nose or a pair of pliers, and you can start to peel the inside layer off. And you just keep heating up the plastic, and you just keep peeling it off, and you can finally get it all off, and you take a sandpaper and sand the first one down. They do not weld together like I had originally thought. So it's like, wow, it was a lot of work. It was an awful lot of work, but we were able to take the broken part off and use the pipe. It's kind of cool. So back to this course, how does this apply to what you're doing? Now, there's a lot of different ways we can do thrust blocks, but I just want you to understand the principle of thrust block. So for your homework problem, you are going to get to solve a momentum principle of a pipe going around an elbow, okay? So we're going to have a pipe come in, and it's going to go around this elbow, all right? And I think I have a reduction in the pipe. I'll have to look. I may change it up a little bit, but flow going in here, and this is in the XY plane. So this is in the horizontal plane. So we're not worried about gravity here. We're not worried about momentum in the Z direction. We're only worried about momentum in the X and the Y, which means then that we are going to have a reaction force here, our X, and we're going to have a reaction force here, our Y, that has to be in place to hold this elbow from moving, okay? And what I want you to do, then now this is maybe not a terribly real problem, but potentially it could be, but it helps you understand the concept. We're going to assume this pipeline is laid out on top of a concrete pad. And the pipeline itself is not on the pad, so there's no friction between the pipe and the concrete, but our thrust block is going to be sitting on the pad. So if you were to look at it from the side view, I want to put a great big old block of concrete. So there's where my pipe is, right here, okay? And I want that concrete block to be large enough to keep that elbow from moving. Okay, so think about this. Let's walk through this in a little more detail. We'll do it on time. We got a few minutes, good. And here's the concrete pad that this whole thing is lying on, down here, all right? What's holding that concrete block in place on that concrete pad? friction. Okay, great. So now we're going back to statics. So we're still doing hydrostatics here, right? Because friction is part of basic statics. How does friction work? What are the equations for friction? Let me ask it that way. What are the equations for friction? Do you remember that? The friction force is equal to what if it's static? The friction force is equal to the static coefficient of friction, mu sub s, times the normal force. Okay, so we have to define what this is, and this is based on property materials. So I'll give you that in the homework problem. The normal force comes from then, Scott, go ahead.
Well, the mass of the concrete block.
The mass, yes, the mass or the weight of the concrete block. So this concrete block has then weight coming down. And that then is going to create a normal force. And this normal force then, if this pipeline is trying to move this over, the normal force or the friction force is going to resist it. So the question now is what force do we use to calculate what is the force that's trying to move this block? It's not the weight force. The weight force creates a normal force. It's sitting there. What is the force that's trying to move the block? Yeah, so these two forces, right? But how, okay, so good. So these two forces are, so we'll say our concrete block here. Which colors would show up on this a little better? We'll work to get all these, well, I guess they're okay, aren't they? So we're putting this concrete block up here. Okay. And so these two, the pipe is pushing on the block's pushing back. Do we calculate for R sub y separately? And then R sub x and take the biggest? If I'm trying to move a fridge and I'm pushing on it this way, and I've got a buddy pushing on it from the side that way, which direction is the fridge going to go? Yeah, it's going to go up an angle, right? So if I've got two forces here from the pipeline pushing on that block, it's not going to go only in the x direction. It's not only going to go in the y direction. So we have to find then the resultant force, R sub r. And by knowing the resultant force acting down here, we can now figure out what this friction force is, or needs to be, would be an appropriate way of saying it. What does it need to be? And if we know what the friction force is, and we know the friction and static coefficient, we can now calculate what is the required normal force. And if we know the required normal force, we can calculate what the weight of that block needs to be. Okay. So I'm going to give you an opportunity to go ahead and calculate a thrust block based on that principle right there. Now, in real life, is that how it really works? Well, it could. If you had a pipe sitting on top of a concrete pad and it wasn't resting on it. Now, if it was resting on the concrete pad, then you'd have additional weight from the pipe itself helping to keep it in place. If the pipe was down in a trench, you would have the soil properties, and soil properties, as you know, are varied. You know, is it clay soil, is it gravel soil? So if you want to take those into account, you could actually reduce the size of your thrust block. But in reality, do you want to spend an hour trying to, well, maybe 2-3 hours, take a sample of your soil, figure out all your soil properties? You just want to pour a couple extra cubic feet of concrete down in that hole and call it good, right? I mean, move on. You got bigger things to calculate. Just make sure, just do a simple calculation, put a big enough thrust block down in there. And normally when we put thrust blocks down on pipes, we normally wrap the pipe with asphalt paper or some other paper to make sure that the concrete doesn't attach to the pipe. Because if we ever have to go back in and fix the pipe, the last thing we want to do is be busting up a bunch of concrete, right? And we don't put the concrete all the way over the top of the pipe, we put it off to the side and bottom. And the soil then becomes a safety factor. Because if we have a transient that comes through this system, and we talked about water hammer, if we have a transient, even if it's small, come through it, that creates really high velocities. Now you have a impact. Like hitting a nail with a hammer, that's an impact force. So you have a high velocity that's there and then it's gone, well, that's an impact force. And you don't want your pipe to move that thrust block because of that. And then a lot of thrust blocks really aren't blocks themselves. If your pipe is hanging up or if it's along a wall, you attach it to your building. You have hangers and clamps that you attach your pipe to hold it in place. Right? Little side note here. This is my ADHD coming through, I guess. If you ever go into a building and you look up and you see a pipe come along and all of a sudden it does a little 90 degree and it goes anywhere from 5 to 8 feet, does another 90 and comes back and then continues. Have you ever seen that? You look up to a building that has open, you say, why did they put this extra pipe in there? Why didn't they just keep going straight? Because the pipe just goes straight, but it's got this little beep, beep, beep. Anyone have any idea why you have that?
I know that they use it in oil pipelines for expansion and contraction.
Yes, right there. Expansion and contraction. Everything expands and contracts with different temperatures, right? So if you've got things that have different temperatures, a pipeline has to expand and contract. Something has to give, because if you don't allow it to give, now you're going to put internal stresses inside of that pipe. And internal stresses can break pipes. So putting this little U-shaped in there allows it to have a little bit of a moment, and it will bend and contract, and it fixes the problem. But people that don't understand, they're like, you wasted a lot of pipe, man. That's a lot of money. 4 elbows, 1, 2, 3, 4 elbows, and some extra pipe, and you could just put another 2-foot piece of pipe in there and went straight. But there's a reason why we have those type of things, right? Okay. All right, any questions on momentum or on thrust block concepts? Because I mean, that's what your homework's going to be on. Maybe I'll give you 2 problems. An ice cube in salt water, seawater, and a thrust block problem, all right? And we can talk about the ice cube one when we get into class next time if you're like struggling with it. Don't spend a lot of time on it. But it is a basic problem that you should be able to solve. Okay. Let's see, we just have a few more minutes here, so don't run off just yet. Okay, so you guys pay good money for this course, right? I want to make sure you get your full amount. We have now talked about fluid principles, control volumes, conservation of mass, conservation of momentum. We haven't covered modeling or dimensional analysis yet, and we really won't go into a lot of detail. We'll use the principles when we get there. But we have one left, conservation of energy. So to give you a little bit of idea where we're headed, we are going to talk, that's what we're going to talk about on Monday, is conservation of energy, which is the energy equation, which, the Newton's equation that we take and put over to the energy equation. I would note that the energy equation is going to be a big chunk of this course, because we're going to do pipes, we're going to do pumps, we're going to do open channel flow, which uses the energy equation. So we are going to take that equation and apply it to a lot of different things. So become very familiar with the energy equation. It's going to be your best buddy now till the end of the semester, right? So that's where we're going. We're finishing up. We have one other component of chapter 3 that we need to finish up. And that kind of deals with the energy equation loosely. It also applies to the momentum equation, but it's a little principle called the energy correction coefficient and the momentum correction coefficient. That's what we'll start on Monday, and then we'll go right into the energy equation. And from there, we'll go into pipelines, single pipelines, which should be a review from fluids. And from single pipelines, we jump over into pipe networks, which is really kind of cool, I think. A lot of fun. So I'm just encouraging you to read your book, all right, chapter 4. Like I say, we're going to finish up chapter 3 on the energy correction coefficient, slide into chapter 4, and move on down through that. So with that, have a great day, have a great weekend, And I will see you on Monday. Your homework will be due on Tuesday, remember, okay? So my kids get mad at me. They say, "Worst professor ever signing homework over the weekend." I don't want to give them their money's worth. You gonna head over to the office with me?
I have class at noon, but I meet you there after.
Sure.
You for Crystal.
Yeah. So you have class at noon or 11?
It's senior design. Oh, I mean 11 until 11.
Oh, that makes sense. Yeah, that's 11.
So I can-
Yeah, so come by. I'll be in my office.
Perfect.
That'll work.
Thank you.
Nico, how goes it?
Yeah, for that one credit class, it's when I try to register the class, it said I need admission, so